My name is Sergey. I work in Tiki in search team, and today I will talk about our Spellchecker implementation, which we find CPU and memory efficient. So here is the results of Tiki for the query iPhone. So this is the top model right now, so you will see it in top. So here is the results if you have the iPhone with a misspelling and without the use of Spellchecker. So you see it's obviously absolutely irrelevant. And here is the results with the same misspelled query with the Spellchecker, just for you to sort of understand how we apply it. Why am I talking about it? Okay, so here is our general approach. Basically, I just try to pseudocode the whole algorithm in here, and then I will split it into the details in each further slide. So we take the input query and we tokenize it. Tokenizer here is very simple. We just tokenize by space symbols, just tokenize into syllables, and we get our input words. And the result initially is just an empty array. And then for every word in the words, we generate a list of candidates for every word with this function, right? Which I will tell about this function later in the further slides. And then we basically pick the best candidate out of here using the function Spellchecker score, which I will also tell in the further slides later. And then, we basically just append the best candidate into the result array. And our final result is just the array of the best candidates for each word. This is very simple to understand, right? Okay, let's go further. So, first of all, about generating candidates, which was this function. So we basically just, for each word in our input array of words, we just generate all possible similar words. So to do that, we have to define the measure of similarity, right? We use Damerau-Levenshtein distance for that. Damerau-Levenshtein distance is defined as an edit distance which allows 4 different types of changes in the word. It allows insertion of the symbol, deletion of the symbol, substitution of one symbol, and transposition of 2 adjacent symbols. So if it's iPhone, P and H, you can change P and H, and it will be the distance 1 from this Damerau-Levenshtein distance perspective. So we use that distance to calculate the similarity between our candidate and our word when we generate the candidates. And we also limit maximum allowed distance depending on the length of the word. So for super short words, we only allow maybe one change from this distance perspective. For longer words, we allow 2 or 3 changes. And then basically we just generate all possible edits with these 4 allowed operations, all possible edits of incoming word of all these 4 possible types, which is obviously CPU greedy because it will bring you a lot of different options, a lot of different candidates. So we will optimize it, but let's talk about it later. So for now, basically, this is just a function to generate candidates. This is easy to understand, right? Okay. So we should go further, right? Okay. So now the Spellchecker score function, which was this function here, which we use to maximize, to pick the best candidate. So we use a standard noisy channel model. There is a lot of things to read more about it, in a more mathematical, in a more strictly mathematical way. But basically, it's just we say, okay, for the set of for the given set of the candidates, we want to find the candidate which maximize this probability, the probability of this candidate being intended when the word W was observed. And we can use Bayesian formula, which is a pretty standard approach of the probability of something if we know that something else happened before. we can like use this multiplication to calculate this probability. And in here, the meaning of this one, of PWC, would be sort of the probability of the word W to be a misspelling of the word C without any other given context. And we will explain later how to calculate this probability using something which we call error model. And P of C, like probability of C, is just the probability to observe the candidate C in like in a real world text or in a real world query. We call it like a language model. And we also explain later how we build this language model to calculate this probability. And PW from Bayesian formula is just a constant for every candidate C. So we can just ignore it. So basically, we just need to maximize this multiplication because PW is a constant for all candidates C. This is easy to understand, right? Okay, let's go further. So first, building the language model, which is to calculate probability of the word C to be observed. So we call it n-gram model. It's a standard approach to build these language models, and it tries to predict the probability to observe the word given a certain context of words before and after it. So how do we build it? Like first of all, we just collect a lot of data. We take all product contents, like all product descriptions in Tiki. We also take all Tiki search queries. We also took some additionally crawled text from the Vietnamese web. And totally we got around like 5.5 compressed texts. So here is an example. Let's say here is our data. Like it's all like queries in Tiki. Just one by one in some big, really big text file, right? And then let's just count them. So let's just write them like, let's say this query, myzemat, happened 200 times. What was funny? And like myzemat happened like just 5 times. Then like, yeah, this query happened 100 times, this 5 times, this 100 times, right? So we just counted all the queries in our input data. And for this example, I just took like some small like artificial input data just to show as an example, because I obviously cannot show like the real huge data in the slides. Okay, so this is easy to understand, right? We just count the queries. Then like we have these queries counted, and we just basically count all possible single words and word pairs which occurred in these counted queries. So let's say, for example, we see that the word my appeared 410 times in here. You can calculate it, like if you want to check. It's 200 plus 100 plus 100 plus 5 plus 5. And like also the word my appeared 410 times in the beginning of sentence. This symbol we use it as a special character for the beginning of the sentence, which is also a context. And then like let's say the word top appeared 105 times in the end of the sentence. You can check it's really like that. It's like 100 times here and 5 times here and both times in the end of the sentence. So yeah, this is also easy to understand, right? We just calculate single word and double word things and how often they appeared. And this dictionary we already call our language model because it lets us to easily calculate the probability of some word, let's say my, given a certain context, given a context before or the context after, or just no context. So let's see the example of this. Let's say here is our language model, which we calculated in the previous step. And let's say the query was my. So with a given context, it will be beginning of sentence, my, end of sentence, right? So we would say that the probability to see my in this context is the average between the probability to see my in the beginning of sentence and probability to see my in the end of sentence, right? We can model like that. So according to our language model, which we just built out of our example data, we can see that the probability to see my in the beginning of sentence is the probability to see my in the beginning of sentence is the count of times we saw my in the beginning of sentence divided by count of times we actually saw the beginning of sentence. And in our language model, it's both 410 times. You can see that we saw beginning of sentence my 410 times, and you can also see, unfortunately, it's not in this example here. Maybe it's just not the last version of the slides, but anyway. You can count it from here. You can just see that we totally have 410 sentences. So in total, we have 410 beginning of sentences. So here, and the probability to see my in the end of sentence is equal to the probability to the count of times we saw my in the end of sentence divided by the count of times we saw end of sentence. So my never happened in the end of sentence in our language model, but the end of sentence happened 410 times because we totally had 410 sentences. So the total probability would be like 0.5 multiplied by 1 plus 0, so it's like 0.5. For this, the probability of the word my happened in this context. Another example, my psi top, and we try to compare candidates for the word psi. We have two candidates, psi and say, and let's calculate using the same technique. So the probability of psi in the context of my and top would be the probability to have psi after my and the probability to have psi before top and average between these two. We can calculate that this one, like my psi, the count of times is 105, and psi total count of times we can, unfortunately, also not in this example, but you can calculate from here. It's 410 times, right? Let me double check it. Sorry, yeah. In here we divide the count of times we saw my psi to the count of times we saw my. So we saw my 410 times and we saw my psi 105 times. So the probability is like this division. And we do the same with the psi top, which is like the number of times we saw psi top divided by the number of times we saw top after this word, which is 5 divided by 105. And the result here would be 0.30. You understand all these calculations, right? Okay, so we can do the same with say. And say, obviously, like if you look into our samples, you can see that say, like actually after my, psi and say happen almost the same amount of times, right? But before top, say happened to be like way more often than psi, right? So that means if we calculate the probability here, this one for psi and for say will be almost the same, but this one for psi is way smaller than this one for say. So in here, as a result, we have 60% probability, while for psi we only had 30%. And this all means basically that language model here suggests that the probability to see say in this context, in the context of my say top, is higher than the probability to see psi in this context. Okay, everybody understood that, right? This is our language model. So this lets us to predict the probability to observe the candidate C. Let's go further. So now about the probability of the word W to be a misspelling for the candidate C. Normally people would just collect big dictionaries of popular misspellings and then try to crawl this probability out of these manually collected dictionaries. But we used an approach which lets us to collect this dictionary automatically and to make it much bigger in size than any manually collected dictionary. And this approach is quite sophisticated. I will go through these steps first, and then I will show an example after that, so maybe you understand better. So the general approach is we use the same set of texts which we used for language model, and we extract triplets out of it. Word 1, word 2, word 3. So we have all these triplets, then we group them by the first and the third word. So like, let's say if the triplet was my say top, and the other triplet was my say top, then we will group them together because my and top, word 1 and word 3, and word 2, like we just group by word 1 and word 3 together. Then we remove the groupings which are not popular, just so they not make noise in our data. Then we remove samples where the words in the middle are too different from each other using our Damerau-Levenshtein distance metric, which I explained before. Then we remove samples where the popularity of the most popular middle word and the less popular middle word are comparable. And then after that, what we have left with is basically the samples where word 1 and word 3 are the same. Word 2 for different samples are really similar to each other, but one of the word 2 is much more popular than other ones. And this looks exactly like a misspelling, right? Just the idea of this. I will give more examples later. Let's try to do with the examples. So again, this is our data, same as like a language model. We count the queries, again the same queries. Then from these queries we collect the triplets. Okay, so basically we just counted the triplets in here. All the triplets which you can see in these counted queries. Okay, after that we group the triplets. So let's say we group the, anything, and the end of the sentence. We have only 2 triplets which can be grouped under this grouping, right? The one is like the mat and the end of the sentence, and another one is the mat and the end of the sentence. Another grouping which we can come up with is my something top, and we also have only 2 triplets which come into this grouping. One is my say top, and another one is my say top. And also, like, we have very simple groupings, like, let's say my something sing, and we only have 1 triplet which is coming under this grouping. It's my say sing. My say sing to, this was the original one, but this is just a triplet. We don't care about the words here. And then sing something end of the sentence also, like sing to end of the sentence, and so on. Like it goes further, but we just have this as an example here. Okay, so we have these groupings, and then if you look at these 2 triplets in this grouping, it's obvious that we can sort of tell that in this context, probably people who have written mat, they actually intended to write mat, right? Because these words are very similar. The context happens like they happen in a similar context, and one is happening much more often than the other one. Okay, so this is basically how we build our error model. Out of this grouping, we can write down that, okay, 200 times we had a story when somebody written mat and they actually intended to write mat. But also 5 times it happened that somebody written mat, but they actually intended to write mat. From this grouping, we can extract the information that 100 times somebody written say, and they actually meant to say, but also 5 times somebody written say, but they actually meant to write say. And from these simpler groupings, we can just extract it like 100 times somebody written say, and they actually meant say, to, and etc. And the format of this error model is like the count of times, the observed word, and the intended word. The count is the number of times that having this observed word, this actual word was intended. So obviously this dictionary will let us to calculate the probability of the word W being a misspelling of the word C. Or let's put it another way, the probability of the word W would be observed if the word C was intended. So let's go to some certain example. So here is our error model, which we calculated in the previous step. And let's say the query was chem the mat. And we have, for mat, we have two candidates to check. One is mat, and another one is mat. So let's try to calculate this probability. Here is our observed word, mat, right? And the first candidate would be also mat. And then the probability to observe, for the word mat to be a misspelling of the word mat is 0. How we calculate it? We just divide the number of times mat was intended when mat was observed in our error model. And we divide it to just the total number of times when mat was observed in our error model. So you can see that mat was observed in our error model total 5 times, right? But it was never intended, it was never in the third column. The third column is intended word. The second column is observed word. It's the same format in here. So we divide 0 by 5, we get 0 probability. Then we try to calculate the probability of the word mat being the misspelling for the word mat. So again, we just divide the number of times the word mat was intended when mat was observed in our error model, which is 5. Here it is. And we divide it just by the number of times when mat was observed in our error model. This is also 5, because this is the only time when we observe mat in our error model. So the probability of mat being a misspelling for mat in our error model, this is just a sample error model, this is not real one. But in our error model, in our sample error model is 1. So what this means is just according to our error model, built on this sample data, it is extremely likely for the word mat to be just a misspelling of the word mat. And this is how we build error model. This is all easy to understand, right?
In this example, how do you know mat is the word to focus on? Why don't you focus on the chem or lượng, but you focus on the last word?
I just, my goal in here, just in one simple slide to show how the error model works. If I show it on chem or there, it won't be that interesting because the error model will show that there is no misspelling for chem or there. It's just correctly spelled words. So basically, there will be only one candidate which is correct. I mean, it's just if you remember, okay, let's go back to the first, let's go back to the first slide. Yeah. As you remember here, we just split the words into words, and then for each word, we pick all the candidates, right? So for chem the mat, we will do the same. We will first pick the word chem, right? We will take all the candidates, maybe 1,000 or 2,000 candidates for it, and for every candidate, we will calculate language model probability and error model probability. Then we multiply, then we found the maximum. Then we say the maximum, what gives the word which gives the candidate which gives the maximum is our correct candidate. Then we move on to the. We do the same. Then we move on to mat. But the point is, for chem and the, I could show the example with error model, but it will be hard to understand how error model works on this example. So that last word mat, it's not that we start working from it. It's just this is the easiest example to explain how the error model works. You understand? Okay. Okay, so yeah, we finished with the error model. So now we can even further optimize the quality of what we came up with, because we assumed that the language model is more important than the error model if we have bigger context. So if we have more words before the word or more words after the word, then probably the weight of the language model in our formula should be bigger. So we try to switch from PWC multiplied by P of C into PWC multiplied by P of C into the power of lambda. And the lambda, we try to just pick different values of lambda for different length of the context before and after. And I won't go deep into the details of this process. But in the end, we saw that if we pick lambda a little bit bigger than 1 for longer context and just 1 for like shorter context, then we have a little bit better results in our tests. So our idea worked. This is just like some simple slide about what we did to optimize the quality of predictions even further. Okay. And then the point is like if we want to use like currently we just use a single word and a 2-word context. If you want to use a longer context, like maybe 3 gram or 4 gram, then we probably will have to use machine learning to pick the better lambda. Currently, we just like picked it manually. We tried a few different values. Okay. Then the performance optimizations. So like the approach which we came up with worked well, but the problem was that it took a lot of CPU and a lot of memory. The CPU, because the way we pick the candidates is very straightforward, and obviously, like it's a combinatorial algorithmic complexity. So there is an important fact which we noticed, and it's like it is possible to prove that if Damerol-Levenshtein distance of W and C is n, then for any W and C, we can find a combination of no more than n one symbol deletes from each side of the word, from V and from C, which will lead to the same result. And here is a few examples. Like let's say the word W was iPhone and the word C was iPhone and the word W was I4B, right? So the distance, the Damerol-Levenshtein distance is 2 because it's 1 insertion and 1 substitution. And then like you can do 1 deletion from iPhone and get this word, and you can do 2 deletions from this word and get this word, and these 2 words match. So like another example, okay, also iPhone and like this weird word, right? Also the distance is 2, 1 transposition and 1 insertion leads from this one to this one. And you can also do 1 deletion from iPhone and get this word, and you can do 2 deletions from this one and get this word. So basically, it can be proven that this idea works. So we want to use this idea to optimize the performance of picking the candidates. How we do it? Okay. So for every word in our original dictionary, which we load in our language model, let's say, for every single word, we pre-compute the dictionary of deletes. So we basically take every single word in our language model and try to delete 1 symbol one by one from each of these words. And for every result of deletion, we say, okay, this deletion maps to this original word in our language model. Then for every incoming word in every incoming query, we also do all possible deletion of 1 or 2 symbols, depending on which distance we allow. And then for every result of these deletions, we try to check which original words in our language model led to the same deletion. That will let us go down from combinatorial complexity to something like n log n complexity. Not really linear, but it's still a lot of candidates, but at least we only work with the candidates which were in our original dictionary, and we have a really fast, like nearly constant way to get these candidates. I don't know. Was it easy to understand this optimization? So basically, using the idea I explained here, instead of like taking every word of incoming query and trying all possible 4 operations and generating all like a huge number of candidates, we just delete symbols out of it, and we also delete the symbols out of our original dictionary, and then try to match using this fact that we can always match using no more than 2 n deletes from each side. Okay. So yeah, like doing that helped us to reach a really good performance. But the problem was that this delete dictionary took a lot of memory. It took around 60 or 70% of whole memory which we used for our spell checker. So the second thing we did is like we just used different data compression techniques, like just we used the dynamic arrays library, which lets us to do even further like integer compression. And by doing that, we managed to go down from 10.5 gigabytes to just 2.3 gigabytes of data for this whole thing with the spell checker data, which was good enough for us. Okay, so testing results. For testing, we picked 5,000 random queries and also 10,000 misspelled queries. The reason why we didn't pick just random queries is because it's a rare case to have a misspelled queries in a random query set. So if we just use random queries for testing, then we could not see any small improvements in our spell checking algorithm because they will be just impossible to see in a so small amount of misspelled queries in a random query set. So we used 5,000 random query just to check that we still perform well on a random query set, which we have in Tiki, and we also have used 10,000 misspelled queries to be able to see small improvements easily. Then we generate suggestions for these 15,000 queries using Google API, and we check them manually. And this was the only place in our whole approach when we needed some manual work. We just wanted to make sure what we did actually works from the expert perspective. And yeah, like we just used only one correct variant per query, which is not always right. Like sometimes one misspelled query could have few different sort of correct options possible. So yeah, but we wanted to use some simple testing approach. So using this testing approach, we proved to be like slightly like 10 to 12% worse than Google. But this is totally okay with our memory requirements, because Google Spell Checker like memory requirement is up to like 100 times bigger. And in A/B test, this approach shown 3 to 9% increase in purchases. So this was also pretty much okay for us, because our main goal was just basically reach this kind of result. And future plans is that maybe we will use a bigger language model data to be able to decrease the this 10 to 12% worse thing than Google. So maybe like get somewhat better quality, which is not necessarily converts to better purchases, but still like it's nicer to have better quality if it gives like a little bit of better business result as well. And yeah, maybe we will use better testing approach, like allow multiple variants from our spell checker, multiple variants in our test set. And yeah, this is basically the future plans. That's it. This applies to any language. The only things which matter is what do you use for training. Like the data I was explaining here. Wait. Nope, not here. Yeah. So I told like this is the data we used, right? So let's say like doesn't matter. Okay, if you only want to this data also can do a really good spell checking for non-toned Vietnamese queries. But even better, even like let's say you want to do a spell checking for Egyptian language, right? You can use absolutely the same code which we written and just use like Egyptian, I don't know, e-commerce website, product descriptions, or even just Egyptian like literature, and like try to build the language model and error model using the same code, using this other data, and it will work. Like maybe not let's say maybe you have to tune some parameters, but in the end it will be applicable to that language. So there was no single place in these slides, in this approach, which depends on the Vietnamese language. It's absolutely language independent.
You have to have different data sets.
Sure, yeah. Of course.
About the data set, we did the wrong data set here. How about the percent of the text you get from the Tiki inside, and the other, the random draw text, the percentage of them?
Yeah, it's a good question. Actually, I don't remember exactly, but I think this one was around 20% only. So mostly it was e-commerce text.
I asked the question because, I read your algorithm and I saw that because when you use the probability, that means if you your universal was the dictionary, it tends to be if the Tiki content to be dominant, so the words from the Tiki content will dominate the others, and then when you suggest, it will tend to choose the correct words that occur in the Tiki data sets.
Sure. Well, mostly we applied to Tiki queries again. So people don't really look for philosophy on Tiki, right? So it sort of works, but if we completely remove this, then it had proven in my experiments to work worse.
One more thing, that the raw text you get from the others, what the type of the website or the content?
Just some popular Vietnamese websites, like news websites, like Zing.
I asked the question because, for the news content like that, it tends to the words is more from the entertainment, something like that. It's not mentioned much about the product.
Sure, yeah.
The brand, the model, the product. And one more thing is that when you choose the Tiki words from the Tiki universal pattern words, something like that. So when you have a new product, it still tend to correct the words to the old one. For the new product, for example, you have the máy kem rửa mặt, but then you have the new product like thuốc nhỏ mắt. So the Mac, because in the example you see, it tends to suggest or correct the word to the Mac, not to Mac, not Mac. But when the new product thuốc rửa mắt, that's not the wrong word.
Yeah.
So I see in the algorithm when you do the score, I don't see how can the algorithm will choose thuốc rửa mắt instead of kem rửa mặt.
For your example, it's your example is the one which will work better if you use bigger data for language model, because you have with the triplet you have the and mat or mat and the end of the query.
Because rửa mặt, thuốc rửa mặt, the people who enter that, they don't mean anything else. But in your data set, you conclude that rửa mặt is more tend to rửa mặt than rửa mắt.
Well, it's just my data set. In my data set, I just come up with some artificial data to show how it works. With your example, I will need to see what's the actual frequencies of people.
Just go to the algorithm. We see that.
Sure.
I don't know how we will solve the problem. Yeah. So when you generate the candidates, I know that you will see thuốc and mắt, and the other one is kem and mắt. So kem and mắt, it tend to be more maybe higher score than thuốc mắt. You see?
Let's use that one. So the query is them.
Let me try that. So actually, that one is not for book. Okay, but in your data set, this one is more higher score than and but when you compare that, because this one is has a higher score, I guess, because for example, in your data set,
well, actually, I mean, like this is just a question of my example data set. I mean, in real data set, probably these two will be very close to each other.
For example, this is the new product. And in your data set, you conclude that the lower score than this one. Very lower score a lot than this one. So how can you choose? I don't see in the algorithm that anything that we choose this one instead of this one.
Well,
even.
I think you mean the time given for the model to learn the work.
No, not the time. It's the problem. Okay. This one. Okay. I exactly mean I want to search for this. But in your data set, I sure this one is lower score than this one because it's a new product. It never happened in Tiki then they sold something like that, right? But in your data set, you train that you get the thuốc rửa mặt is so many products of this. So maybe this one will be a higher score, right?
might be, yeah.
Sure, it's sure, not maybe, because this is the old. You have many products like this in Tiki, but this one is just a new product and never happened before. So how can you choose this?
Well,
this.
Okay, so if you obviously are talking about real data already, you are far beyond my very stupid simple data set. So in real data, like imagine this and this happens the same amount of time in real life. Like if you talk about new product, it's okay. We just retrain our model sometimes. So new product, if it happens, we like at some point we just retrain. So this is not the problem of new or old product. But what you also say is that let's imagine that this is sort of correct query for some users and this is sort of correct query for other users. Well, I mean, in real life, imagine the situation that this and this are equally likely. Like let's say 50% are searching for this and 50% are searching for this. And then somebody types this, but he actually means this. If there is no other context, that for any algorithm is absolutely impossible to understand that he actually means this while he is typing this. Because there is no any user data which proves that this should be preferred in a certain context or in a certain situation to this. So like the example you are talking about, yeah, of course, I mean like sometimes these probabilistic algorithms doesn't work. But the example you are talking about is super specific. I mean, like, no, I'm not sure like what is the real situation because I'm not fluent Vietnamese.
What I mean is, okay, for both of them, they will have, even for this, the later have a higher score. Mm-hmm. But in this context, you should suggest the product of thuốc rửa mặt before this the later.
Why?
Because they enter the correct. I mean, we have to respect what the user query. If that's the correct one, you have to suggest the product of this first and then the other later. You got it?
I don't understand. Like.
I think what he meant is this talk is about misspelling. Then what happens if the user not misspelling? Then
we just suggest like what he actually originally written. Like for everything which user type through this noisy channel which we use to model the misspelling, it is possible that noisy channel produce exactly what he wrote, but it is also possible that the noisy channel produce something misspelled. So if user typed something correctly, our algorithm with a certain quality, which we explained in the resulting slides, will suggest what he actually typed as a correct option. I mean, we don't always correct. You know, like we sometimes give the same result as an input.
I'm not sure I understand that. So let's come up with an absolutely simple example. We have 1 million product. Let's say nước rửa mặt. The second one, yeah. And we only have one product. Sữa rửa mặt. Thuốc rửa mặt. Yeah. So the ratio is 1 million to 1. If the user search for the specific first product, then what would the system suggest? Is that
okay? I got it. Like, the reality is that it's really unlikely to meet the examples which you are explaining. It's really easy to come up with your mind that it might be possible, but actually it's almost impossible. But I will tell you a funny story. So basically, like, there is a label. It's called anchor, right? This label produced some sort of USB logs or something. I mean, I don't remember, but it's like sort of famous. I'm not sure, like maybe Chinese brand or something. Oh, sorry. Anyway, so there is another brand, and it's called AUKEY. And the product set of this brand is 95% similar to the product set of this brand. But this brand is maybe 10 times less popular than this brand. So this is ANKER. It's just like some, I mean, I didn't know it before I actually met this case with the spell checker. And this one is okay. So basically our spell checker suggests that this is a misspelling for this one. Which is understandable, because this is much less popular brand, which has absolutely the same set of products as this brand. So basically it looks like a Chinese fake of this one, right? I mean,
I understand, but the case of this point is to respect the user input before to consider this to be a misspell.
Well, I mean, you have to sort to come up with a metric of your success, right? And then, of course, if you have the measure of your success in respecting users, then you can include that measure into this calculation. And then you maybe come up with a different model. But if we just talk about some generic, understanding of like and respecting what user wanted to type, then it's impossible to measure. I mean, you can always say that there is one case when we have to respect what user originally typed. But this doesn't work in general. I mean, we can just always respect what user type and we will never be able to do any misspellings, right?
So actually I'm curious about...
Maybe I don't understand what you ask. Yeah, maybe I just didn't understand what you asked.
Okay, let me rephrase that. So how is the new system collaborating with the original one to just search but not machine learning and all that stuff? How do your new system work with the old system? So I assume that when a user input a query, then it will go to your machine learning checking first, then it tries to correct the query to something else, and then use that to input into the database search, Elasticsearch or something like that. Is that correct?
Well, we use both original and corrected variants in search.
So how can you put them together?
Just 50-50 right now. We can actually come up with the weights, but 50-50 works well because actually in most cases, the only one variant which our spell checker suggests is actually correct. And then that means that for incorrect variant, most likely there is just no results. But actually we can come up with the weights out of this whole approach. We were just too lazy to implement because it already works quite all right. I mean, we can later come up with the weights. So like if we sort of like 100% sure if it's a misspelling, then we give like, let's say 90% weight to the corrected variant and 10% to the original. If we are sort of not sure, we give like 50-50. If we are like slightly sure that maybe there is a misspelling, then we give like 10% to correct variant and 90% to original. But yeah, we use both variants in search rate.
So by 50-50, you mean you fetch that query into both system and...
There is no two system. There is only one system. We just modify the Elasticsearch query. So we like send both original and corrected variant, and we use them as like, you know, Elasticsearch. They have different ways to do that, like shoot query, like Boolean query, and also like function score. Like they have like, I mean, I don't want to go into Elasticsearch details here.
So you will actually send two queries into the...
One query with like two options inside one query. I mean, Elasticsearch query is a huge JSON thing. And it has like a lot of different subqueries and sub-subqueries inside. And it's all called like one Elasticsearch query. I mean, yeah, we send two queries if it's easier to understand.
I think in that case, it will solve our problem because there is an exact match for the first product.
I think I got what you mean. Yeah, thank you. Sorry. I mean, yeah, you meant that like maybe it's still like, I mean, some small probability that this is like sort of legit. And yeah, we obviously use both options in search now. We could later, I mean, as I explained, we could later come up with different weights for different certainty of spell checking. But for now, we always just use both original and spell checked one.
So we also rely on the scoring of Elasticsearch or something like that.
Sure. Yeah. Sure.
Another question. So I just came out. So how do you like correct the success metric for your algorithm? So because you show both, right? You show the exact match and also the result based on the spell checking. And how do you know? How do you decide to correct the success metric? How do you know that okay, your success is correct or not?
I'm not sure I understood the question.
So maybe because in order to validate your algorithm, the system, right, you need to correct the metric in order to know why you know okay, your spell checking is correct, or it's just some random and user don't really click on it or something. So how do you correct it? Based on the user decision to buy the product after they click on like a product which were corrected based on your spell check or something else.
Okay, for releasing, like when we released this thing, we just did A/B test a few times, like on small audience first, then on like full audience. And as I told, we saw like 3 to 9% increase in purchases. So that was the reason why we decided to release it. That's it, like really.
So you just like A/B testing, which means your first version is without spell checking, and your second version is with spell checking, and you see the increase in revenue.
Yep.
Yeah.
Sure. Before that, as I told, we had like a set of 5,000 random queries and 10,000 misspelled queries, for which we collected the correct spelling beforehand manually, and we just had a marker test. Like we basically just go through these 15,000 queries and check how often our spell checker brings the correct result. No, we checked manually. After, we did Google before to make the manual work easier, but we checked everything manually afterwards.
One more thing about the algorithm, did you have you ever considered any other algorithm, something like
So, well, like the reason why I like end up using this approach is like when I was working in CopCop, what we did for spell checking there was like extremely dictionary based and heuristic based, and with much bigger data. I think with like we used around 30 gigabytes of memory for spell checker in CopCop. It ended up having like just very slightly better quality than this approach, which we reached with like basically 2 gigabytes of RAM. This approach seemed to be nice because I'm sure it's the approach which is still used in Google. They came up, started using it from 2009 or 2010, I think, and it's also language independent. It also doesn't need any supervision. Like it just trains on the data directly. So it's basically pretty easy to implement. It's proven to be working really well in Google, and it doesn't need to do any manual work, except if you want experts to have these 15,000 queries to check later before you release.
How long for the training to get the two model, the error model and the language model?
It is pretty quick. Like, I mean, I also implemented it in C, I think, but it's, I think on these 5.5 gigabytes, it takes maybe 3 or 4 hours to train both language and error models.
And how often do you do the?
Actually, not that often currently, but yeah, we should come up with some data flow to do it regularly.
Content will grow.
Yeah, sure. Currently, we just manually do it sometimes. Yeah, like we need.
I have a question. Why did you choose the language model for check spelling? Do you have another approaches? Do you have another approach or any other approach?
You mean like why did we choose this thing? As I just replied, like we just chose it because it's used in Google and it's proven to be working well for like 10 years, and it doesn't need any supervision. It just needs the data, no need to manual work to teach it, and it's easy to implement. Like these 3 components.
Do you know other approach to?
Yeah, as I told, like in CopCop, we used a little bit different approach, which is also language dependent. It only will work for Vietnamese language because inside the algorithm, they had a lot of code which like optimization for, like, let's say, okay, let's keep like 2 dictionaries, one with the tones, another with the removed tones, and let's also say that these particular, like, let's come up with a different distance, which depends on how you type text and telex, which is nice. I mean, it's nice to have, but in the end, having this like beautiful sort of approach and having it working with almost the same quality, and actually like with the possibility to use the same amount of resources and make it to do the better quality is in the end nicer, I think. So yeah, like I know a few other approaches, like even like we tried to do like before I joined, the guys tried to do some deep learning approach in here, but then like I guess it maybe just required way more data to reach a certain level of quality. So we end up with like this approach. Sure. Like in CopCop, in my previous company, we did. And also in Tiki, before I joined, they also did. Like in here, before they tried deep learning. Ok. Thì trước anh join Tiki, thì ở đây đã thử một cái approach là deep learning. Còn tại CopCop thì anh cũng thử một cái approach mà kiểu là nói thế nào? Dùng rất nhiều heuristic, không cần rất nhiều manual data để học. I'm not sure, maybe like impossible to understand what I just said. For this one, actually, there was literally no machine learning in this approach in terms of like optimizing something. So machine learning is basically when you have a lot of coefficients, sort of, or like a lot of like degrees of freedom, and you have some data, which, and you can like, you sort of use some mathematical thing to sort of pick the right values for these degrees of freedom to reach the best results on your data, right? So there was literally nothing like that in this. We can come up with some machine learning in here. When I was talking about when I was talking about quality optimizations. So in here, like we said, okay, we can use lambda power for language model. So if we have like 3 gram or 4 gram, like more context before and after, then we will have a lot of lambdas. Because if like we use 4 words before and 4 words after, then we have to use like bigger lambda, because it's more like the language model becomes more important than the error model. So in here we will have around maybe like 20 different lambdas, and this is already a good thing for machine learning, because you just cannot manually, you know, optimize 20 different coefficients. But in our case, we only had like 1 context before, 1 after, and then like no context. Even in our case, impossible to have no context, because begin and the end is also a context in our model. So we only have like 3 different lambdas, and we just manually played with them to prove that our idea works. We didn't really go deep into it, because like we just wanted to quickly come up with some working approach which gives us better, you know, customer retention and better transactions. We might later obviously do this machine learning thing, but in here, like right now, there is no machine learning. Wait, they will bring the mic.
How lambda is calculated and what is the context of in the first sentence language model is more important in bigger context. So what is the context mean?
Context is just the number of words before the word you try to predict and the number of words after you try to predict. So let's say, for example, if your query is just my, then like you only can apply language model with the one, like with the beginning of the sentence before and the end of the sentence after, right? So like you don't know if it's like blah 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 my, or it's just like my. I mean, like you don't have the context. And then in that case, the error model is more important for the score. We thought, and we checked, and it proved to be like that. So why we thought that? Because we think that just like by the way the language works, like when you type something, the word you type after actually depends on the word you have typed before. And then like the success of all these Markov chain model like used in natural language processing proves that, right? So like you can successfully model like really complicated things using this simple idea. So like the context here is just like if you let's say have 4 words before the word you try to predict, then you should give bigger weight to the probability to meet this word having these words before than to just the probability of this word being misspelling for another word, right? I mean, does that make sense? It just we picked it. I mean, like this is where machine learning comes, if we want to. Like for us, we just picked, like we said, okay, let's try lambdas 1, 1, and 1. We have only 3 lambdas. 1 lambda is for 1 context before, 1 lambda is 1 context after, and 1 lambda is like for before and after. Like we have both sides, we have the word. So we said first, let's try 1, 1, 1. Okay, we checked, we get some result. Then we said, okay, let's try 1.1, 1, and 1.5. 1.5 for context from the both sides. And we have better result. We said, okay, let's try 1, 1, and 2. And we had the same result as 1, 1, and 1.5. Then we say, okay, let's try different. So we just basically brute force a few coefficients just to sort of like prove that the idea works. That led us later to use a proper machine learning in here to actually get like bigger and better results out of this idea. But for now, we just sort of proven to ourselves that this idea works.
You A/B testing for validate your algorithm, but actually for e-commerce, it's effective by season. Is it more Christmas or holiday? So can you say how you validate exactly? I mean,
Sure.
effective is by algorithm or is by sales season?
Sure. So when you do A/B testing, you actually compare two algorithms at the same time. So, like strictly speaking, it might be the case that I don't know. Let's say for the seasonal queries, let's say it might be the case that in the season of big sales, people tend to make 3 times more misspellings than usual, right? And if you A/B test during the sales season, then you see, oh, okay, we get a good result because they misspell so much, so we spell check and correct so much, and then we get bigger transaction, and then sales season go off, and then they stop. They only type correct queries, and then there is no point in you spell checking anymore. But we believe it's not the case. So we sort of trust that if we A/B test 2 algorithms at the same time, we in the end we will get an honest comparison as a result. But if you have any idea how it really could be that the season might affect the spell checking, please suggest. I mean, I don't have anything in mind with how it could be. Sure. No, we just did in parallel over a period of 1 month. I think did 2 or 3 different tests.